Okay, hi guys. This is going to be a small recap of all the equations in IGCSE Physics for board exams in 2023. And this includes space physics, which is an addition from last year's syllabus. All right, let's get started. First off, we have motion equations of motion. So first we have velocity, which is nothing but displacement by time. One thing to note is that displacement is a vector quantity and speed is a scalar quantity, and speed is equal to distance by time while velocity is equal to displacement by time. So using that simple logic, we get that velocity is a displacement is a vector quantity while speed is a scalar quantity. Average velocity is equal to the total displacement by the total time, and the more commonly used one would be the average speed, which is equal to total distance by total time. All right, and a is equal to v minus u by t. That's a pretty simple equation. It's nothing but the rate at which velocity changes, and rate basically brings in the idea of time. And mathematically speaking, acceleration is the derivative of velocity in respect to time, and velocity is the derivative of displacement in respect to time, and therefore acceleration is nothing but the second derivative of displacement in respect to time. That is just mathematically speaking. Then you have these two simple equations: weight is equal to mass into gravity and force is equal to mass into acceleration. And from this, by simply comparing those two equations, we see that mass is constant, but A is equal to G and F is equal to W, which basically implies that weight is the force acting on an object when the only is weight is the force an object experiences when gravity is the only accelerating force acting on it. And the value for gravity on Earth as accelerating force is 9.81 meters per second squared, while the field strength of the Earth is 9.81 newtons per kg. These are some further motion equations which are not necessary for us in IGCSE, but these can be helpful. I like to call these the SUVAT equations, SUVAT, where S is displacement, initial velocity, final velocity, acceleration, and time. And if you notice, these four are vector quantities, and this is a scalar quantity. All right, this will come in handy next year in A levels when you will actually have to. So if you have something like this, launching it like this is theta. You have to separate this force into its vector quantities. So this will be cos theta, sine theta, right? That is why these will come in handy, because all of them will have an x and y component while time will only be a scalar quantity. And these are just the equations for them, which we don't need to go in depth for. Then you have density, moment, forces, and pressure. This is density, mass by volume, and it is measured in kg per meter cubed. Pressure is equal to force by area, so it's measured in newtons per meter squared, and 1 newton per meter squared is equal to 1 pascal. And in liquids, it is equal to rho gh, density into gravity into height. And this gravity is the field strength, 9.81 newtons per kg. Force is equal to k delta x, which is Hooke's law. K is the spring constant, delta x is the displacement of the spring, and force is the force in the spring. The spring is observing. And the moment of force is equal to perpendicular distance into force applied, and it is measured in Newton meters. Momentum is equal to mass into velocity, and it is measured in kg meters per second. And we later get to know that that is the same thing as 1 Newton second. We can do the derivation in the later slide. In an isolated system, momentum initially is equal to the final momentum. And in an isolated system, there is no exchange of matter and there's no exchange of energy either with the surroundings. In a closed system, there is exchange of energy, but there's no exchange of matter. And in an open system, there is an exchange of energy and matter. So when it's an isolated system, which is what we will be under the assumption of in IGCSE physics, there'll be the conservation of momentum, meaning that the final and initial momentum will be the same. Then we have forces in equilibrium, where the opposite forces will basically counter each other, meaning that they have to be of the same magnitude but in the opposite direction. And this is where we get the idea of force in terms of momentum. So simply deriving this, we get F is equal to ma, that's Newton's second law. Acceleration is nothing but v minus u by time taken, which can then be written as mv minus mu divided by t, which is nothing but delta p by t. So we get force is equal to the change in momentum per unit time, or by the time taken. And therefore we get one more unit, which is impulse. Ft is equal to delta p. This is where, sorry, This is where we get the idea that impulse is nothing but newtons into seconds, right? So 1 Newton second, um, yeah, this is Newton second. Okay, this is measured in Newton seconds, and this is measured in kilogram meters per second, and they're the same thing basically. Now, energy, work done is nothing but energy, and is the same thing, is measured in joules, and this is nothing but force into distance. Or, and in the later classes you'll get cosine theta involved, which will make sure that it's only perpendicular distance. So basically, as work done is a scalar quantity, we can use distance instead of displacement. So in the later classes, we'll get work done is equal to force into distance into cosine theta, which will be the angle, to make sure that it's only the horizontal perpendicular distance that you're making sure that you're counting. Then you have kinetic energy is equal to mv squared by 2, potential energy, which, gravitational potential energy, which is equal to mgh, and elastic potential energy is equal to k delta x squared divided by 2. Delta x is again the displacement, k is the spring constant divided by 2. And in an isolated system, energy is conserved. That's the idea, right? If you go back, we see that in an isolated system, energy is conserved, and it's the only system where energy is conserved, and that is why it's only in the isolated system. And what happens is that as kinetic energy gains, there's a gain in kinetic energy, potential energy decreases. As the potential energy increases, kinetic energy decreases. And a very good example of that would be something like a pendulum. So if you have something like this is a pendulum, this is a pendulum. It has its maximum speed right about here. This is Vmax. Vmax means that its kinetic energy is maximum. Kinetic energy is max, right? Simple logic, because mv squared by 2, maximum. Over here, potential energy is max, which means that kinetic energy is 0. And over here, we have kinetic energy max, which means that potential energy is 0. Simple conversion. Like I said, rate at which energy is transferred or rate at which work is done is nothing but power. It is measured in joules per second or watts. Thermal physics, we have E is equal to mc delta T, E is equal to ml, and the conversion between Kelvin and degree Celsius. This value over here, 0 Kelvin, is absolute 0, and that's it. E is equal to ml, L is latent heat, and latent heat in general is the energy needed to change the state of a unit mass by from, let's say, liquid to solid. Sorry, solid to liquid. That will be fusion, and latent heat of vaporization will be from liquid to gas. That's it. C in this case is specific heat capacity, which is nothing but the energy needed to increase the temperature of a substance by 1 degree Celsius when it has a weight of 1 kg. And a faster or a better way to say this would be the energy change needed to increase the temperature for unit mass by 1 degree Celsius or even 1 Kelvin, because the conversion between them, if you have 1 Kelvin and 1 Kelvin is going to be equal to what? Minus 272 degrees Celsius. So what we see, the change between them is 1. So therefore 1 Kelvin is equal to 1 degree Celsius. When it comes to conversion between them, they are not, but an increment of 1 Kelvin is equal to an increment in 1 degree Celsius. This is what I mean by that. PV is equal to nRT. Well, you don't have this equation in IGCSE, but this basically shows us that pressure is directly proportional to temperature, volume is directly proportional to temperature, but pressure and volume are inversely proportional to each other. N is the number of moles, R is the molar gas constant. So these are just two constants that we don't care about right now. Then we have waves, where we have v is equal to f lambda, v is velocity, f is frequency, and lambda is wavelength. Frequency is measured in 1 by second, or second to the power minus 1, or hertz. When it comes to reflection, we have sin I is equal to sin r, or simply the angle of incidence is equal to the angle of reflection. That's it. Refraction index, or it should be refractive index over here, is nothing but the refractive index of the first medium multiplied with this angle of incidence, sine of the angle of incidence. N2 is this refractive index of the second medium multiplied with sine r, which is the refraction angle of refraction. And therefore, with this, if with this we can get the idea that sine I by sine r is equal to what? N2 by N1. If you use this logic, then if N1 is air, meaning that the initial medium was air, we can get the idea that it has a refractive index of 0, so we just cancel this out. The refractive index of a medium when light is traveling from air to the second medium is equal to sine I by sine r. This is Snell's law. Then you have n is equal to 1 by sine c. C is the critical angle, which is the angle of incidence at which the incident wave or the incident wave basically gets refracted perpendicular to the normal, and there's some form of total internal reflection also taking place. And then you have n is equal to c by v, where in this case c is the speed of light in vacuum, which is 3 times 10 to the power 8 meters per second, and v is the speed of light in that specific medium. Then I have a mnemonic over here for the electromagnetic spectrum, which I used, which is real monkeys insist very useful Xmas gifts. And this visible light over here that we see, if you remember, if you notice, infrared means, well, there's red hidden over here, which means that when you start writing VibGyor or the opposite of whatever it is, red is going to be on the top and violet is going to be on the bottom, because ultraviolet, right? So that is one way to remember it. And another thing is that this order is of increasing frequency. As you go down, it's increasing frequency, increasing energy, but decreasing wavelength. Energy and frequency are directly proportional to each other. Then you have electricity and magnetism. Charge is equal to the current into time, and therefore current is equal to charge by time. Resistance is equal to voltage by current. Power is equal to current into voltage. Energy is equal to current into voltage into time, because energy is nothing but power into time. And potential difference and electric potential, basically voltage, is equal to work done by charge quantity, which basically means joules per coulomb. If you have a transformer over here and a transformer over here, there will be turns on both of them, right? The number of turns is normally not equal, because that's only then will there be actual use of a transformer. Basically, the ratio of the voltage between these two is equal to the ratio of the turns between them, and the power between them is conserved. However, if it's a step up transformer, then there'll be more turns on this, meaning that the voltage on this will be greater, meaning that the current on this will be lower. And if it's step down, then the voltage on this will be lower, current on this will be higher. One thing to know is that if it's a step up transformer, that means that the voltage is higher, current is lower. As the current is lower, there'll be a lower temperature of the wire. The wire will be at a lower temperature, which means that there'll be greater conductivity or lower resistivity. And lower resistivity means that there'll be a greater efficiency of transfer of energy. That is why when it's over a long distance, we use the step up transformer on one side to basically increase the efficiency of the transfer of energy. Then you have nuclear physics, which basically starts off with basic chemistry. We have protons, neutrons, and electrons, charge of 1, 0, 1 minus respectively, and a mass of 1 mu, 1 mu, and 1 by 1840 mu. One important thing, well, not important, but one very interesting thing is that protons and neutrons are actually not fundamental particles. They are made up of quarks, up quark and down quark. And if you want to research on that further, I'll let you know that a proton is made up of 2 up quarks and 1 down quark, while a neutron is made of 1 up quark and 2 down quarks. Electrons fall under the field of leptons. Then you have the decay. Firstly, you have the particles, alpha particles, beta particles, and gamma radiation. Gamma radiation is nothing but the gamma waves from the electromagnetic spectrum. So they have a charge of 0, speed of light, mass of 0, and they have no ionizing effect but are very, very, very penetrating. They have the highest penetrating effect of these three particles. Alpha particles are basically the helium nuclei. They have a speed of 0.07 c, so they're the slowest of them all, and they have a charge of 2 plus because they're helium nuclei. Mass of 4 atomic mass units because they have 2 protons and 2 neutrons. They are very ionizing but have a very low penetrating ability. Beta particles have a charge of -1 and are basically electrons. They have a speed of 0.6 to 0.7 c. They have a mass of, well, this mass, and have a low ionizing effect but a higher penetrating ability than alpha particles. Then you have the nuclear decay equations. Basically, in alpha decay, we have the emission of a helium nuclei, and so you'll have to subtract 4 from the mass number and 2 from the atomic number. Then you have gamma decay. This asterisk over here basically symbolizes the presence of the element in its excited state, and it's going to emit gamma radiation to get lost, to lose that extra energy that it has. And then you have beta decay, in which a neutron gets converted into an electron and proton, and so the mass number stays constant but atomic number increases. And this is basically the general equation. But note that there are two types of beta decay. There's beta positive decay and beta negative decay. Don't need to go any depth about that. Just remember this equation over here. Now we have space physics, which is the addition, and we have the average orbital speed, which is nothing but 2 pi r by t, and 1 by t, which is 1 by time period, is nothing but 2 pi rf. Is going to be frequency. 1 by t is equal to frequency, and 1 by f is equal to t. Then you have the Hubble constant h sub 0, which is the ratio between the speed at which the galaxy is moving away from the Earth and the distance from the Earth, and it has a value of 2.2 times 10 to the power minus 18 seconds. And well, this equation over here, if you reciprocate it, then you get this equation over here, which can have its own uses. And well, that's it. Thank you for watching.